So this is a recording of me going over the answers to your practice midterm exam. And I not only wanted to go over the answers, but then a little bit of explanation and reteaching as well. So from Unit 1, the first question, what is a heterogeneous mixture? Well, if you will remember, hetero is the prefix that means different. And mixture means that these are not pure, which means it's not an element or a compound, and they're things that you actively mix together. So as we look through this mixture of possible answers, a couple of things stand out. First off, I see gold here, and I see this symbol. That symbol is from our periodic table, and since it's from the periodic table, I know that that is an element. Another thing I notice, I see sugar, and I see all of this. And all of that, those are element symbols that are from the periodic table, but that's not an element because I have multiple elements in a formula. And since I have multiple elements in a formula, I know that sugar is a compound. So by process of elimination, I know the answer is not B or C. So that leaves me with either paint or Italian dressing. Now, for the overwhelming majority of us, if you pick up some paint, it appears uniform, meaning that it appears the same. And if you pick up a bottle of Italian dressing, it separates into an oil layer, and a water layer. And then there's like spices and stuff floating around. So which one of those sounds like it has different things in it? Well, it's the Italian dressing because I can see these things. I can see that there's different things all together. That's what allows me to say that it's Italian dressing and not paint. So all of that is my explanation to question 1. So the next question, if you were given a mixture of sand, iron, and salt, how would you separate the substances? And then what physical properties were most useful in separating the mixture? Well, let's kind of start by talking about what each of these things are. So sand, iron, and salt. So what do I know about sand? Well, it's kind of brown in color, small, it doesn't dissolve, I know, because otherwise we would not have sand beaches because they would just dissolve in the ocean. What do I know about iron? It's a metal, it's kind of silvery dark colored, and it's magnetic. And what do I know about salt? Well, it's white crystals. It's also small, but it does dissolve in water. So I've got 3 different solids. Which one of these should I get out first? Well, I think we should get rid of the iron first. So I would use a magnet to remove the iron. So for the iron, the thing that's the most important is that it's magnetic. And then I'm going to look at the sand and the salt. And between the sand and the salt, they're both small, which is frustrating. But the thing that is most important here is that sand doesn't dissolve and salt does dissolve. So my next step is I would add water to dissolve the salt. Once my salt is dissolved, I would pour through a filter or a strainer of some sort and catch the sand. The salt water goes through. And then my last step would be to evaporate the water. Okay, so moving on. Question 3. An object has a volume of 6 centimeters cubed and a mass of 3 grams. What is its density? So if you don't remember the density formula, you should probably draw this triangle on your note card. It's arranged the same way as the states in our area. So Maryland is on top of Virginia with DC in the middle. So DMV. So I am looking for density. So if I cover up density, what is my formula left? Well, it's mass divided by volume. Okay, so I've got D equals M over V. So my mass is 3 grams. My volume is 6 centimeters cubed. 3 divided by 6 is 0.5, and the correct unit for density here is grams/centimeters cubed. Now, will the item float or sink in water? Well, we had to remember that water has a density of 1.0 grams per centimeter cubed, and that if something is going to float, it is smaller than 1.0, and if it's going to sink, it is larger than 1.0. So our density of 0.5 is smaller, so this thing is going to float in water. Moving on to Unit 2. Okay, so I've got some temperature conversions here. So 400 degrees Celsius into Kelvin and 32 Kelvin into Celsius. So if I need a Kelvin temperature, it is the degrees Celsius plus 273. And if I need the Celsius temperature, it is the Kelvin minus 273. So in this first one, I have Celsius. I'm looking for Kelvin. So I am adding 273 to that temperature. So that would be 673 degrees Kelvin. Now for this next one, I'm giving you Kelvin and I am asking for Celsius. So I will subtract 273. Do note that I have a small number, 32, and I am subtracting a large number, 273. So I will have a negative answer, and you must write that negative symbol down. So negative 241 degrees Celsius. Okay, next question. Calculate the amount of heat needed to increase the temperature of 300 grams of water from 27 degrees Celsius to 50 degrees Celsius. So let's try and label everything here. The amount of heat is Q. Increase the temperature of 300 grams. That is a mass. I have a temperature of water from 27 degrees Celsius, so that's where I start. And I'm going to 50 degrees Celsius, which means that is where I am finishing. So I see Q, I see M, and I see my two temperatures. Now, I will not do this to you on the test. I neglected to give you the specific heat of water, which is C. That's 4.184 joules per gram degrees Celsius. The formula I am working with is Q equals M times C times delta T. My recommendation, if you do not remember that formula, put it on your note card. So first off, my first step was always to calculate my delta T, which is temperature final minus the temperature initial. So here that would be 50 minus 27, so that is 23 degrees Celsius. And then I'm going to plug everything into the formula. So Q equals my mass of 300 grams times my specific heat of water times my delta T, which I just calculated. So I've got all those numbers, and it's 300 times 4.184 times 23. And that answer should give me 28,869.6 is the number, and the unit for heat is J, joules. Okay, a pot of hot water was cooled in a refrigerator. Explain why the water was able to cool. Include a diagram and particle motion. Okay, so I've got a fridge, got a shelf, got a pot of hot water. So I'm going to say it's red. Okay, so what is happening here? You have to remember there is no such thing as cold. There is only heat and the absence of heat. So I do not want you talking about cold particles. So we can talk about fast particles and we can talk about slow particles. So the pot of hot water has fast particles. The air in the refrigerator has cold or slow particles. See, I just did the thing I said not to do. These are slow particles. So what is going to happen? Well, these fast particles are going to be leaving out, right? And as they are leaving out, they're going to bump into the slow particles. Okay, so fast particles collide with slow particles in the air. Right? The fast particles slow down, which decreases their temperature. The slow particles speed up, which increases their temperature. And that's how that's going to happen. Okay, so on to the back side. Unit 3. We have one liquid, liquid A, evaporates faster than another B. Which has the stronger intermolecular attractions, and how do you know? So remember, fast evaporation means it is easy to separate from the liquid to become a gas. That's what it means to evaporate. You are leaving the liquid and becoming a gas. So it's easy to do that. So which one of these has stronger attractions, the liquid or the gas? Well, the liquid has stronger attractions. So if it's easy to separate from the liquid, that means those attractions must not be very strong. So if it's easy to separate from the liquid to become a gas, that means you must have weak attractions. So who had the easier time evaporating? Liquid A did. So liquid A must have weak attractions. And liquid B must have strong attractions. And if you go back to the lab in the heating and cooling curve packet where we talk about this very lab, remember that I said you should think about water on your skin. Sure, you feel it, you kind of feel it evaporating, you blow on it, it blows a little more, but if you put like acetone on your skin, it evaporates so fast and it makes your skin really, really cold, okay? Because acetone is a really weak attraction and it evaporates very, very quickly. Okay, so if this is the curve for substance A, what would the substance B look like? Well, B has stronger attractions. Stronger attractions does mean a higher boiling point and a higher melting point. So if A was there, well, let's say I just do that, and I just draw B right on top of it, but shifted up, right? B is shifted up all the way because it's got the stronger attractions, means it requires more energy. Okay, so moving up a little bit more. As the temperature of a gas increases, all right, so we're talking temperature increases, so that means faster, harder collisions. What's happening to my pressure? Well, faster, harder collisions is the definition of an increase in pressure. So if temperature goes up, pressure goes up. And that was Gay-Lussac's law. Okay, so as the pressure of a gas increases, so that means more frequent and harder collisions. That's what pressure means. So what's going to happen to my volume? Well, if the pressure of a gas increases, then the volume of that gas is going to decrease, right? So this is going to squeeze, squeeze, squeeze. You got to remember that this is talking about squeezing. All right? So again, think about a balloon, and I've got my particles inside, and if I've got pressure increasing, right? Pressure increasing, pressure increasing. That is going to squeeze that down. So this was Boyle's law. And as you remember, pressure increase means volume is going to decrease. All right, moving on to the most recent stuff. So it says, describe the difference between J.J. Thomson's model of the atom and Rutherford's. So J.J. Thomson, this was like the blueberry muffin or the chocolate chip cookie. So basically we have positive dough, all right? So that is just positive stuff. It's not space, it's stuff. We just don't know what it is. And then we have these little negative electrons, okay? Because he gave us the electrons. Now, when we come along to Rutherford, well, Rutherford condenses all of that positive stuff into a tiny little space. So now we have, instead of stuff, we have positive nucleus. And then those electrons, well, they're all around here on the outside. Okay, so these are still my electrons. And then all of this, well, that's just empty space. So the main thing to kind of think about is if you have like blueberry muffin dough, I said if you pull out all the little blueberries and you take the remaining muffin dough and you just like squish it all up into a tiny, tiny, tiny little ball and then leave the blueberries scattered around it, well, that's how you take Thomson's model and convert it into Rutherford's. Okay, it says Rutherford was not able to simply draw a new picture of an atom and change the way everyone thinks of matter. What evidence did Rutherford use to convince the world we need to change how we envision atoms? So again, this is the gold foil experiment. This is the most important experiment for you to know for the exam. And again, I'm going to draw here. We've got a little piece of gold foil. We have the actual apparatus that he used outside. We have our alpha particles, and you have to remember that alpha particles are positive. We fire those alpha particles, and then we see three things happen. Boom. Number one, most pass through, proving empty space. All right. That's what proves that an atom is mostly empty space, because everything just passed through it. Number two, we get some deflection. All right, so particles deflect away, proving they passed by something positive. Because again, the alpha particles are positive and like charges repel. All right, and then the last thing is every once in a while, these alpha particles would bounce straight back. And if you bounce straight back, it's like they hit something dense and massive. And it is this dense, massive thing, these two things here, which Rutherford combines together to call the nucleus. So that's the experimental evidence that Rutherford used to change his model. And then lastly, let's talk about protons, neutrons, and electrons. So pick your favorite element. Well, I don't know that I have a favorite, but I am really fond of boron because I think it's fun to say. So write its element notation. Okay, so boron has the symbol B, and it's got an atomic number 5. Okay, so this is my atomic number. And what does the atomic number tell me? Well, the atomic number tells me that this thing has 5 protons. Okay, so boron, let's say I'm talking about boron 11. And remember that 11 there, well, that's a mass number. So where does that go in my symbol? Well, it goes up here. So that's my mass number. And my mass number is the protons plus the neutrons. So if I have 5 protons, how many neutrons do I have? Well, I've got 11 minus 5, or 6 neutrons. Now, I'm going to assume that most of the time, unless I tell you that I have a net charge of 0, because otherwise, you do not know yet how to figure out charges on your own. So I have to tell you. So this is the net charge. And again, our net charge was protons minus electrons. So if I have a net charge of 0, what that means is that my protons equal my electrons. So at this point, I have 5 negative electrons. And that's how we go through that process.